Hello and welcome to video number 15 in this series. And in this video I'm going to review some examples of simplifying complicated expressions that use a lot of the ideas that we've looked at in previous videos. So for a first example, I want to see if I can simplify this expression. And the reason I want to try and simplify it is I'd like to know what happens to this expression as the value of h goes towards 0. And I can't really do that in the form it's in at the moment because we've got h in the denominator, and if h was 0, this expression wouldn't exist. So let's see if we can figure out what this expression might look like, and then we might be able to determine what happens to it when h goes to 0. So just looking at the expression, I think the only thing I can do initially is expand what's in the numerator and then go from there. So I have to expand x plus h squared, so I'll have x squared plus 2xh plus h squared, and then I'm subtracting x squared, and I'm dividing all that by h. So one thing I notice is I've got an x squared there and a minus x squared there. So, and then the other thing I notice is what's left, I've got a common factor of h in the numerator. So I've got h times 2x plus another h. And then I see that I have an h in the numerator and the denominator. So this simplifies to 2x plus h. And so now I can look at this expression and I see that as h goes towards 0, this expression goes towards 2x. And I wouldn't have been able to figure that out just looking at this expression before I simplified it. Let's do a similar example where again we're trying to figure out what the function does as h goes towards 0. So for this one I'm going to bring in some square roots. So square root of x plus h minus square root of x, all divided by h. And again, I don't know what happens to this expression as h goes towards 0 because I've got h in the denominator and that kind of messes things up. So instead, let's see what I can do here. So when I've got square roots like this, and I've got the difference between two square roots, I can use the idea of a conjugate to see if I can make some headway. So what I'm going to do is take the expression as written, and then I'm going to multiply by the conjugate of the numerator. So that's the same thing, just with the plus sign. And then if I do the same thing in the denominator, this fraction is just 1. So I'm not changing the value of this thing, but maybe I can make a little bit of headway in simplifying it. So now, now I've got an expression that I need to expand. So I've got square root of x plus h times another square root of x plus h. So that will just be x plus h. And then I've got the square root of x times the square root of x plus h with a negative sign. But I've also got square root of x plus h times the square root of x with a positive sign. So those two will cancel out. That's the idea behind using conjugates, is some of the partial products end up cancelling each other. And then the only other piece I have to worry about is minus square root of x times plus square root of x. So that's just minus x. And then in the denominator, I've got h times this piece here. So square root of x plus h plus square root of x. And then now I see that I've got x minus x, so those cancel. And I'm left with an h in the numerator and an h in the denominator, so those cancel too. So I'm left with 1 in the numerator and square root of x plus h plus square root of x in the denominator. And now, if I look at this and I ask myself what happens to this expression as h goes towards 0, then square root of x plus h is going to go towards square root of x. I've got another square root of x, so this whole expression will tend towards 1 over 2 square root of x as h goes towards 0. Let's do a third example. I'm going to keep track of the examples here so we don't get lost. So that we had first example and then second example and then third example is going to be 1 over x plus h minus 1 over x all over h. Okay, so here in my numerator I've got two rational expressions and I'm subtracting them, so I need to think back to how to do that. So how to do that is to use common denominators. So I'll have 1 over x plus h times x over x minus, and then x plus h over x plus h times 1 over x, and that whole thing is divided by h. And so in the numerator I've got an x minus an x minus an h, all divided by x plus h times x, and that whole thing is divided by h. So in the numerator I've got x minus h, so those x's are going to cancel. So I'm going to have minus, and then I've got h divided by, so this is in the denominator, the x plus h over x, and I've also got this in the denominator. So I'll just write it like this, and now I can cancel the h's, and I'm left with minus 1 over x plus h times x. And that, as h goes towards 0, will become minus 1 over x squared. Let's think about a different kind of example now. Let's think about this expression. So So 3 over x plus 2 minus 3 over a plus 2, and all divided by x minus a. And in this example, I want to figure out what happens to this expression as the value of x goes towards the constant a. And unless I do something to this expression, I don't know what happens, because if x goes towards a, the denominator goes towards 0, and again, this thing does not exist at 0 for when the denominator is 0. So I need to simplify this before I do that. So this one's a little bit similar to the last one, because I've got the difference between two rational expressions in the numerator, so I'm going to have to find a common denominator. So 3 and then x plus 2 times a plus 2 over a plus 2, and then subtract, and let's do x plus 2 over x plus 2, multiply that by 3 over a plus 2, and that whole thing is divided by x minus a. And next, so I've got 3a, and I've got 6, and I've got minus 3x, and I've got minus 6. And then I've got x plus 2 times a plus 2 in the denominator, and I've also got x minus a. So I'm just going to collect those all together just to make this a little bit neater. So I've got x minus a, and I've got x plus 2, and I've got a plus 2. So the 6's cancel, the plus 6 and the minus 6. And I've got 3a minus 3x. So I'm going to write that. I'm going to factor out the 3, but I'm also going to factor out a negative sign, because I notice down here I've got x minus a. Okay, see how I've got minus 3x, and minus 3 times minus a, I got plus 3a. And I got x minus a, and x plus 2, and a plus 2. And now I can cancel the x minus a in the numerator and the denominator. And I've ended up with minus 3 over x plus 2, a plus 2. And as x goes towards a, this is going to tend towards minus 3 over a plus 2 squared. Okay, let's do one last example with what's going to look like a horrendous expression initially, and it is a little bit complicated, but these are the kinds of expressions that you may have to deal with moving forward. So it's nice to get some practice in simplifying complicated expressions. So let's write this up here. We got 4x squared, and then we got x minus 3, and I'm going to bring in a rational exponent, 1/2. Then I'm going to subtract x cubed. I'm going to throw in a constant of 1/2 in there. And then I've got x minus 3. And I'm going to throw in a negative 1/2 for the exponent. And then I'll put in another constant, a 4, and I'll divide that whole thing by x minus 3, and we'll raise that to the power 1/2, and then we'll raise the whole thing to the power 3. So not a very pleasant expression to look at, but let's see if we can work with it and simplify it a little bit. So where to start? So I notice that I've got x minus 3 in 3 different places in each piece. And I've got some x's, I've got some constants. In the denominator here, I know I've got an x minus 3 to the half and then cubed, so that's going to be x minus 3 to the 3 over 2. It's often a good idea whenever you see fractional exponents like this to try and get rid of them somehow. And one way to do that is if I was to multiply this piece of the expression by x minus 3 to the half, then x minus 3 to the half times x minus 3 to the half would be just x minus 3. So let's see if by doing that we can make any progress. So essentially what I'm going to do is multiply this whole thing by x minus 3 over x minus 3 to the half. Because I'm just multiplying by 1, so I'm not changing the value of this expression, but hopefully I can make some progress. So if I think first about this first term, the x minus 3 to the halves will just collapse into x minus 3. And then this next piece, I'm going to put the 4 here and the half here together. So 1/2 times 4 is 2. And there's not a lot I can do with the x cubed yet, so I'll just pull the 2 out in front. And then I've got x minus 3 to the minus 1/2 times x minus 3 to the plus 1/2. So that's just going to reduce down to the number 1, because I'm going to have, remember when we're multiplying numbers with exponents, we add the exponents. So minus 1/2 plus 1/2 is 0, and if we have an exponent of 0, then the number becomes just the number 1. So I don't even need to write it down because I'm just multiplying by 1 at this point. So it's already looking quite a bit better. In the denominator, I've got x minus 3 to the 3 over 2 times x minus 3 to the 1/2. So that's going to be x minus 3 to the 3 over 2 plus 1/2, which is 2. And so I think all that's left is for us to clean up the numerator. So I got 4x cubed minus 2x cubed. So I've got 2x cubed. And then I've got minus 12x squared. And then I can pull out a common factor here of 2x squared. And I'll have x minus 6. Okay, so a couple of things left here is whenever we're dealing with rational expressions, we have to think about the domain, and the expression is not going to be defined if the denominator is 0. But because we've got some fractional exponents here, we also have to make sure that what's inside a fractional exponent term has to be greater than 0. So because we have x minus 3 raised to the power 1/2 here, we know that x is going to have to be bigger than 3. So x has to be bigger than 3 here. And that takes care of the x is not going to be able to be 3 either. But if x is bigger than 3, then it can't be 3. So this is going to be the domain restriction. So we're good for all x greater than 3. And then why do we even do this kind of thing? Well, one reason we might do this kind of thing is we're often looking to see when an expression like this is equal to 0, which effectively means the numerator being equal to 0. And so in this initial form that the expression was in, it's very hard to see where the numerator is equal to 0. But now that we've simplified it to this form, we can see right away, well, if x was 6, then this expression would be 0. And that's called finding the root of an equation when we're trying to find when it's equal to 0. So the root of this expression is x equals 6. If we weren't paying attention, we might say, well, x equals 0 is also a root. But x has to be bigger than 3, so x equals 0 is kind of irrelevant here. This expression is only defined for x bigger than 3, so the only root is x equals 6. So at this point, we've gone through 5 different examples, getting a little bit more complicated as we go along. So I'm going to give you a couple of examples now to work through by yourself, and pause the video, work through these examples and see if you can come up with the answers. So for the first one, let's do x plus 2 over x minus a plus 2 over a, and divide by x minus a. So this is kind of similar to example number 4. So work with this expression and try and simplify it and get it to a different form in which we can figure out what the expression is tending towards as x goes towards a. And then for the other one, the second one is going to be a little bit more like this one, so a little bit hairier. So let's do 3x plus 2 to the half, and then 2x plus 3 to the minus 1, and then constant 2 minus 2x plus 3, and then let's have a constant of 1/2, and then a 3x plus 2, and an exponent of minus 1/2, and this whole thing divided by 3x plus 2 to the 1/2. Okay, so let's see how you did. Let's do the first one. So looking at the numerator, we're taking the difference of 2 rational expressions, so we need to get common denominators going here. So the common denominator will be xa. So we'll have x plus 2 over x times a over a minus a plus 2 over a times x over x, and all of that divided by x minus a. And so in my denominator, I'm going to have xa and x minus a. And in my numerator, I'm going to have a times x, 2 times a, minus a times x, minus 2 times x. And then in my denominator, I've got a, x, and x minus a. Okay, so I can see that the ax minus ax will cancel, and I've got 2a minus 2x. And again, I'm going to do the same thing I did in the previous example. I'll pull out a factor of minus 2 so that I can write x minus a. And then we got a, x, x minus a. Now I can cancel the x minus a's. And my final answer is minus 2 over ax. And so as x goes towards a, that's going to go, this expression will go towards minus 2 over a squared. So the second one, there's a lot going on here. So we've got to kind of go slow and steady. One thing to notice is we've got a positive exponent here and a negative one here. And then similarly for this term here, we've got a positive exponent here of 1 that's hidden, and then a negative exponent here. So the way that to think about this is really a rational expression, just written in a slightly different way. So it's 3x plus 2 to the 1/2 divided by 2x plus 3. And then we've got a 2 here, so let me put the 2 there. And then this piece, there's 2x plus 3 divided by 3x plus 2 to the 1/2. And then this 1/2, we can think of this as having a 2 in the denominator piece. So we'll put the 2 there. And then that whole thing is divided by 3x plus 2 to the 1/2. Okay, so I haven't really done any simplifying yet. All I've done is change the way I've written this down. Because now that it's written like this, we see that we need to do common denominators to be able to subtract these two rational expressions. So the common denominator is going to be 2x plus 3 times 2 times 3x plus 2 to the 1/2. And because it's in the denominator, I'll combine it with the other expression that's also in the denominator, 3x plus 2 to the 1/2. And though that 3x plus 2 to the 1/2 here and here will just combine and write down 3x plus 2. So in the denominator, we're going to have 2 and then 2x plus 3 and then 3x plus 2. And next, so in the numerator now, So I've got my 2 times 3x plus 2 to the half, and I have to multiply that by, let's see, another 2 and a 3x plus 2 to the half. So the 2 2's will become 4, and the 3x plus 2 to the half times 3x plus 2 to the half will become 3x plus 2. And then I'm subtracting. So here I've got 2x plus 3, and I need to multiply that by another 2x plus 3. So 2x plus 3 squared. Okay, so next let's simplify the numerator. So I think I can go right here. So we're going to have 12x and 8. And then I need to expand this. So 2x times 2x would be 4x squared. And then we've got 2x times 3, which would be 6x. And then 3 times 2x, which would be another 6x. So we've got minus 12x. And then finally we got 3 times 3, 9. So we got minus 9. And then let's collect terms. Hey, look at that, the 12x's go away. So we've got minus 4x squared, and then we got plus 8 minus 9, so we got minus 1. So I want to write this as minus, and then 4x squared plus 1. So that takes care of the minus 4x squared minus 1. And then in the denominator, we've just got what we had before. So 2x plus 3, and 3x plus 2. And let's think about the domain, because we always need to worry about the domain when we're dealing with rational expressions or complicated expressions like this, where we've got things in the denominator. And so we want to, and also when we have fractional exponents. So for this one, if I'm looking at this 1/2 exponent here, I need 3x plus 2 to be positive, which means x is going to have to be bigger than minus 2/3. So let's just write that here. For all x bigger than minus 2/3. Let's just see if there's any other restrictions around there. X bigger than minus 2/3 will be okay for this piece as well, and for this piece, and for this piece. And in terms of the denominator being potentially 0, as long as x is bigger than minus 2/3, we're okay. So there's our domain. And then why would we even do all this? As with this example, it's typically because we want to find out where the roots of the expression are. In other words, where does this expression equal 0? So the numerator of this expression equaling 0, well, that's really hard to figure out. We can easily look at this form of the expression, though, and see that the numerator of this expression will never be 0. Because x squared has to be greater than or equal to 0. So the smallest it could be is 0, but we've got the plus 1 here. So we cannot make this expression 0. So this expression has no roots. So that's all for this video. So in the next video, we'll start moving into a different area and start thinking about solving equations. And we'll start with linear functions. So in the next video, we'll change direction and start thinking about solving equations, and in particular, we'll start with linear equations.